This NMR challenge we have taken from Pavia Spectroscopy book 4th edition. Page number is 226, problem is 15. We have to determine the structure of organic compound having molecular formula C5H10O1 from the given spectral data such as IR values, normal carbon, NMR, depth 135, depth 90 and 1H NMR spectra. Okay, now we are going to solve this problem step by step. So first step is to see the IR value. So we have given two IR value. The one is around 3340 per centimeter, which is a broad peak. So this indicates the presence of hydroxy group in the molecule, and we have one oxygen also, so it could be belongs to the hydroxy. Okay, now second value is 1651 per centimeter. This value indicates the presence of carbon double bond carbon of alkene, because for the benzene it comes from 1400 to 1600 per centimeter. Okay, now we are going to calculate index of hydrogen deficiency. The formula is 2C plus 2 plus nitrogen minus number of hydrogen minus halogen divided by 2. So 2 multiplied by 5 plus 2 plus 0, 10 hydrogen, 0 halogen divided by 2. So index of hydrogen deficiency is 1 degree of unsaturation. So this compound has 1 degree of unsaturation. It is very important to verify your index of hydrogen deficiency value one more time, because incorrect value will mislead your whole structural analysis. This 1 degree of unsaturation value we can attribute to carbon double bond carbon of the alkene. Okay, now let's look at the 13C NMR. We can write the 13C NMR in a graphical form. So we have 1, 2, 3, 4, 5 signals. 1, 2, 3, 4, 5. So all carbons are showing the signals. It means the molecule does not have any symmetry. Now let's look at the depth 135. So in depth 135, this signal is positive. So for sure it belongs to the methyl group. This 40, it is in the negative phase. So it means this signal it belongs to the CH2. And this signal 60 is also in the negative. So it also belongs to the CH2. And it probably attached to the oxygen because it is coming in around the 60 ppm. 112 is also in the negative. So it is very interesting to see that this is highly deshielded region, right? This one is highly deshielded region, and this one is coming in the negative phase. So why it is so? Because there is no benzene ring, right? Usually this region belongs to the benzene ring, but there is no benzene ring. But we know that carbon double bond carbon of alkenes can also come here. Okay, and this signal is missing quaternary carbon. It means 142 is quaternary carbon. It means the alkene, one of the double bond of carbon of the alkene is quaternary. It means it does not have any hydrogen, and this one is CH2. So from depth 135 we can clearly say that this compound has this moiety, and CH3, CH2 and OCH2. Now look at the depth 90. In depth 90 all are showing no peak, no peaks. It means this molecule does not have CH. This molecule does not have any methane carbon. Okay, so we have CH3, one CH2, this is another CH2, and this one is here. Okay, so this, let's say this is 4. So we have this part which we are getting from the carbon NMR data. Now let's look at the 1H NMR data. Okay, so there are, how many peaks are there? A, B, C, D, E. So there are 5 types of hydrogens. Okay, 5 signals means there are 5 types of hydrogen. So signal A is around 1. Let's say 1.7 ppm, somewhere around 1.7 ppm, and this is singlet and corresponding to 3 hydrogen. So how many neighboring hydrogens is 0, and this indicates that there is a methyl group. Okay, now let's look at the signal B, which is somewhere around 2.2 ppm, let's say 2.2 ppm, and this is broad. Yeah, it looks broad signal, and it corresponds to 1 hydrogen. So this could be belongs to the hydroxy group. This is possible that it can be belongs to the hydroxy group. Now let's look at the signal C, which is around 2.4 ppm, and this is triplet, very sharp triplet, corresponding to 2 hydrogens. So triplet means there is a 2 hydrogen in the neighboring, and this is CH2 connected with the CH2, right? That's why it is showing triplet. And now look at the signal D, which is around 3.3 3.8 ppm, and it is triplet. This is also integrating two hydrogens, so this triplet indicating that there are two hydrogen in the neighboring. So this CH2 is attached to CH2, and it is connected to some electronegative atom, and which electronegative atom we have? Oxygen. So it is possible that it can be like this, OH attached to CH2. And now last signal is E, which is around 5 ppm, and this is looks like a doublet integrating two hydrogens. But it could be possible that it can be two different hydrogens, right, which have very close chemical shift value. So right now we cannot say it is actually doublet or two different hydrogens. Okay, so we have following information. This has methyl hydroxy, and this part actually is here. Okay, this is common part. So it has methyl hydroxy, and third is this part. Okay, now we are going to combine this information which we are collecting from the proton NMR and the carbon NMR, and let's see what we will get. Okay, so from carbon NMR we obtain following information: that this compound has carbon, double bond carbon, which is quaternary, and one is CH2, right, which is coming around 112 ppm. Then it has methyl CH2, which is coming around 62 ppm, right, and CH2. And from the 1H NMR we obtained this information that it has OH, CH2, CH2, methyl, and OH. Now we can combine these two informations in such a way that we should remove the common informations and bring it together in such a way that it should satisfy index of hydrogen deficiency, molecular formula, and spectral data. Okay, so we can write it like this: CH double bond C, and this is quaternary, so there is some substituents. Okay, then we have CH2, 1 2 3 4, and this is OH. Okay, so this could be CH3 methyl, because this compound has one methyl group, right? Now it has 1 degree of unsaturation. Yes, let's see if it is satisfying the carbon NMR. So this one will be around 112 ppm, right? And this is quaternary, so it is 142 ppm. This one will be CH2, which is 40.9, yeah, 40.9 ppm, and this is attached to the oxygen, so it will be 60.2 ppm. So it is fully consistent with the carbon NMR, and this methyl will be 22.2 ppm. Okay, now it is fully consistent with the 13C carbon NMR data. Now let's look at 1H NMR. If it is the correct structure, then it should be fully consistent with the 1H NMR as well, right? Okay, so this methyl will give you a signal which is singlet, right? Because there is no neighboring hydrogen. And now B, this hydrogen will give you signal B, and C is a triplet which is coming around 2.3 ppm. Triplet. Okay, so this will be triplet C signal, and it will be triplet because of this CH2, yeah, neighboring CH2. So this is C, and D, this one is D, which is triplet. This triplet is because of the coupling with the proton, this one C, yeah, they are coupling with each other. And OH is not coupling with the CH2. OH is not coupling with the CH2 because of this OH is exchangeable, so that's why it is not showing any coupling. Okay, now this is very interesting part. This CH, now it is E signal. You understand? This is E. This one is known as geminal hydrogens, and for geminal hydrogen J value is very low, 0 to 3 Hertz. Therefore each hydrogen, let's say this is 1, this is 2, so H1 should show doublet which should have value from 0 to 3 Hertz, and H2 also should show doublet which should have low value from 0 to 3 Hertz. Since this value is very low, that's why you are seeing as a 2 sharp singlet, right? And H1 and H2 have close chemical shift value, therefore you are seeing as a doublet like this. But if you run this NMR in a high resolution like 50 megahertz, then you must see the signal like this. This is one doublet, then this will be another doublet, and then one can be H1 and another can be H2, but you are seeing it like a singlet and singlet because this is low resolution 1H NMR. So now you understand that this signal E is belongs to this geminal proton, and this have close chemical shift value. That's why we cannot say these two hydrogens and this is not a doublet. Okay, now this is the correct structure because it is fully consistent with the 1H NMR and 13C NMR and following the index of hydrogen deficiency as well. So that's all for today. I hope this video helped to strengthen your NMR skills. Keep practicing because mastery comes with consistency. And I will see you in the next video with the another exciting NMR challenge. Make sure to subscribe so you don't miss it. Till then, take care. Bye bye.